So in this clip, we will look at what we call link budget. So this is in terms of mobile or wireless communications, where we have transmitter which transmit the signal through the transmit antennas. The signal will be propagated right to the receiver and will enter the receiver to the receive antenna. And because due to the distance between transmitter and the receiver, there gonna be loss or signal loss or degradations along the way. So LP denote loss due to propagations or what we call path loss. At the receiver, we're gonna measure the quality of the signal using signal to noise ratio. So this is a number which is the ratio between the receive power and the noise power. So the receive power could be in terms of milliwatt and noise could be in terms of milliwatt. So that means signal to noise ratio has no unit. Okay, and most of the time we express signal to noise ratio in terms of log scale or dB scale. So SNR in terms of dB, right, or log scale, it's equal to the receive power in terms of dBm minus noise in terms of dBm, right? So dBm is log scale. We can convert a milliwatt into log scale. Now at the receiver, the signal to noise ratio has to be bigger than certain number so that the receiver will be able to detect the message from the signal. Now with this requirement, we can go back and analyze how much transmit power do we need in order for signal to noise ratio to be bigger than certain dB. For example, it could be 10 dB, right? And the question is, what should be the transmit power? Okay. Now, if we look at the relationship between transmit power and the receive power, we see that transmit power, right? Since there's a loss due to propagation or path loss, right? So it's divided by LP, but the transmitter may have the amplifier, or the transmit antennas could amplify the signal, and the gain due to amplifying or due to the antenna at the transmitter is captured by this gain GTX. And the receiver could be, there could be amplifier which amplify the signal at the receiver, right? And also the receive antennas could boost the signal as well, and the gain due to that can be captured by this number GRX. Okay, so GTX, GRX are the gains, and this has no unit. Okay, and at the transmitter, right, the signal go to cable or the feed, and there could be certain loss, right? The power could be lost due to the equipment or the cables, and the loss at the receiver as well. Okay, and so at the end, with all this gain and loss, multiply or divide with PT, you get the receive power. So for this gain and loss, there's no unit. No unit. Okay. PT, usually we do it in terms of milliwatt. So that means PR gonna have the same unit, which is in terms of milliwatt. Okay. And normally we express all this power in terms of dB scale or log scale. So we can see that PR or receive power in terms of dB scale or dBm is equal to 10 multiplied with log base 10 of the receive power in milliwatt. Okay, and we can plug in the relationship that we got earlier. Okay, so this bunch, right, or these terms GTX, GRX, LTX, LRX, and LP has no unit multiplied with PT in terms of milliwatt. And due to the property of log of a product, you can split it into the sum of the two log. Okay. and you do the same thing with each gain and loss, and you see that uh, we can express uh, receive power in terms of dBm is equal to transmit power in terms of dBm. Okay, and the gain, right, we can convert into log scale as well. So it's 10 log base 10 of GT. That's GT in terms of dB, right? So gain at the receiver, that's become GRX in terms of dB. Now the loss, instead of divisions, we're gonna have subtractions. So minus LTX in terms of dB minus LRX in terms of dB, and also the loss due to propagations of path loss in terms of dB. Okay. Now, if you compare these equations, which we do it in log scale, you see that it's either add or subtract terms, which is easier than if we do it in terms of regular scale. Regular scale, you have to multiply and divide, but in terms of log scale or dB scale, you just add or subtract. Next, we will focus on this term, which is what we call path loss. Okay, so path loss, right? This is the loss due to propagations. This is one kind of fading or signal fading, which we call large scale fading. It's large scale fading because the distance need to be in meters or bigger than meters or bigger than wavelength, so that we'll see effects to this path loss, right? So it's large scale. There are certain fading which we call small scale fading. In that case, even small distance can induce signal loss, right? So we'll talk about small scale fading later, but for here we're gonna focus on large scale fading. Okay, so we go back to the same setup. We have transmitter, we have receiver. Okay, and we're gonna say the distance between the two is dTXRX. Okay, and we're gonna focus first on the distance close to the transmitter. So here the distance that is very close to the transmitter, I'm gonna denote it with D break, or the breakpoint distance. So what is this breakpoint distance? It's the distance within very close to the transmitter where the propagations behave, or characters of degradations of the signal behave like it's a free space. Because you know that very close to the transmit antennas, there might not be any objects, right? There's no tree, there's no people, there's no building, so there's no obstructions of the signal. So the signal can propagate very easily, just like in space. Okay, but later on, right, distance beyond this breakpoint distance, they're gonna be building, right? They're gonna be people, they're gonna be trees, and the signal loss will be at a bigger rate. Okay, so first we're gonna let D to be distant from the transmitter. So in the first case, we're gonna focus when distance from the transmitter is less than the breakpoint distance, or what we call D break. Okay, so D break will be a certain distance from the transmitter. This gonna depends on different channel models will have different breakpoint distance. Okay, or different environment, we have different breakpoint distance. It could be 10 meters, it could be 5 meters, right? It could be 12 meters away from the transmitter. Okay, so the loss that is follow the loss in free space, we're gonna denote it by L1. So L1 is the loss from the distance from the base station or from the transmitter to distance D. L1 can be computed by this equation. So 4 pi multiplied with D divided by lambda raised to power 2. So lambda is the wavelength of the signal, right? D is the distance. So distance is in terms of meter, and wavelength is the unit is meter too. 4 pi, that's a constant, there's no unit. So meter divided by meter, that means the loss here, right, in the first part, which is due to free space, this standard is, less than d break, there's no unit. Okay, we can convert lambda, right, into frequency. If you remember the formula, c is equal to f multiplied with lambda. So c is the speed of the light, which is the speed of the wave. We use electromagnetic wave, so it's close to the speed of light. So c is speed of light equal to f, which is the carrier frequency, multiplied by lambda, which is the wavelength of the signal. Okay, so lambda is equal to c divided by f. We replace that, we're gonna get another formula here. Okay, so 4 pi multiplied with d multiplied with carrier frequency divided by c raised to power 2. Okay, and again, usually we're gonna express this loss in terms of dB. Okay, so L1 in terms of dB is 10 log base 10 of L1. Now L1 we can just input this equations in. So 4 pi is a constant, c is another constant, which equal to 3 multiplied with 10 to the power of 8, right? If you recall this, speed of light. Now d, usually we it's in terms of meter, but if we express in terms of kilometer, then it's d in terms of kilometer multiplied with 10 to the power of 3. Okay, f, it's carrier frequency. It's when we talk about wireless or radio frequency, it's in terms of megahertz or gigahertz. So if we express f in terms of gigahertz, then we multiply with 10 to the power of 9. Okay, and this raised to power of 2. Now if you combine all this constant, 4 pi c 10 to the power of 3, 10 to the power of 9 raised to power of 2, right, with 10 log base 10, you get 92.4 plus the other two variable, right? So with the power of 2, so we get 20 log base 10 of f in terms of gigahertz plus 20 log base 10 of d in terms of kilometer. So you see that the loss in the first part consists of a constant, and it depends on the carrier frequency. If the frequency is bigger, the loss will be bigger. Same as the distance is. If the distance is bigger, the loss will be bigger as well. Okay. The second part, right, where the distance is gonna be beyond the free space, right? So it's beyond breakpoint distance, and the loss will be much greater rate than the loss at the first part. So the power for the second part of the distance will be proportional to the distance raised to power of minus n. Or the bigger the distance, the bigger the smaller the power, right? Or the power is linearly proportional to 1 over d raised to power of n, where n, this is what we call paired-law exponents. So depending on the environment, n is between 2 and 4. So 2 is when it's the loss behaving like the free space loss. If n is close to 4, that means there's a lot of objects in the signal path. That's buildings, people, which gonna degrade the signal power. Okay, so we can analyze the loss of this second part, right, as it's a ratio between the power at the breakpoint distance divided by the power at the receiver. So this is the power at dTXRX. Remember, dTXRX is the distance from the transmitter to the receiver. Okay, so due to this relationship, we can say that the loss of the second part is dTXRX divided by d breakpoint raised to power of n. Okay, and again we can convert this in terms of dB scaling, right? So it's 10 log base 10 of of L2, which is dTxRx divided by d brake raised to power n. Okay, with the property of log, you can take the power exponent or the power down and it become multiplier. So 10 multiplied with n log base 10 of this ratio. Okay, so if we combine the two, then we get path loss, right? The total path loss, or LP in terms of dB, consists of the loss in the first part, which is due to free space, loss in the first few meters from the transmitters, and the loss second part of the paths of the propagations, okay, which is at the bigger or higher rate. Now we can look at what happened at the receiver. So the receivers is it's electronic equipment. So there are gonna be electrons which is moving in the circuit or in the cables, right? All this movement of electrons will create noise, right? So we can sort of analyze the noise power which gonna disrupt the signal at the receiver, right? So the noise power, it's in terms of watt or milliwatt, right? Can be analyzed, or it's equal to N0, right? Multiply with B multiply with F. So what is N0? So N0 is noise density, right? So how dense is the noise? This is in watt or milliwatt per hertz, right? Okay. This is a constant which can be computed using this formula. So it's KB. This is Boltzmann constant multiplied with the temperatures in Kelvin. Okay, so Boltzmann constant, you can look this up in the book, right? Multiply with T. It's if the temperature is bigger, there's a lot more movement of electrons, and the noise density will be bigger. Okay, B, this is the bandwidth of the transmission, the bandwidth that we are interested in. This is in terms of hertz. Okay, so if we are talking about wide bandwidth, then there's going to be more noise. Okay, F is what we call noise figure. Okay, so that's no unit, right? So noise figure, it's characters of the receiver. If that receiver has bigger noise figure, that means it's gonna amplify the noise, so you're gonna have higher noise power. If the receiver is it's very good, then the noise figure will be small. Okay, and again, we usually express the noise in terms of in dB scale, or in terms of dBm, right? So dBm is 10 log base 10 of noise in milliwatt. Okay, so if we plug in this formula, right? N0 multiply with B multiply with F, due to the property of log, we can split it into the sum of 3 logs. So 10 log base 10 of the noise density, right? Plus 10 log base 10 of B in terms of hertz, and 10 log base 10 of the noise figure. Okay, so 10 log base 10 of noise density, right? That is dBm per hertz, right? So it's dB scaling. 10 log base 10 of B, right? Bandwidth in terms of hertz, we can express that in terms of dB hertz, right? And then 10 log base 10 of F, that's the noise figure in terms of dB. Okay, so with this we can compute the noise power in terms of dBm. Okay, now we put everything together. Okay, so we'll start from the transmitter. The transmitter will transmit with certain power, or PT. This is in terms of milliwatt or dBm. Okay, and then it's gonna go to the transmitter, which certain signal power will be lost. So the power will go down, right? How much did it go down for? It depends on the loss at the transmitter in terms of dB. And there might be amplifier, or the transmit antenna will amplify the signal with the gain GT in terms of dB. So the signal will be boosted. And then the big part of the signal will be gone due to pad loss, right? So LP or pad loss is the big loss, and you see that they're going to be a big drop, right? At the receiver, right? The receiver might have amplifier which is going to amplify the signal, the received signal power, right? With this gain GRX in dB, and there's going to be the loss. There's going to be some loss at the receiver, right? And that's going to be characterized by this LRXdB. So at the end, the receiver will receive this much signal power of PR in terms of dBm. Okay, and remember at the receiver, it's going to be disrupted by noise, right? So the noise will be N, right, in terms of dBm. Okay, so the difference between PR and N, this is signal to noise ratio. This is in terms of dB. Now, if the receiver has certain specification, for example, it need signal to noise ratio need to be bigger than maybe 10 dB in order for the receiver to be able to detect and decode the signal, right, that it received. Then you can look at this diagram, and then we can trace all the way back to the transmit power what this need to be in order for the receiver to have at least, you know, signal to noise ratio equal to 10 dB, right? And the way we analyze this, this is what we call link budget, right? So at the end, we want to know, right, what is the proper transmit power that need to be there.